Okay, so today we're going to officially start with the integral calculus. So if you've been following in the textbook, we've just finished the derivatives and application of derivatives. So that's antiderivative. That was the last bit that we covered last week. So now we're on this new chapter, chapter 5 on integrals. And you can see the first one here, areas and distances over there. Okay, if you did the reading over the weekend, you would have read through this first bit here. So we're going to go over the area problem. We should be doing a couple of examples today, but then most of the examples we will cover on Thursday, and the more difficult problems on Thursday. And then that will be it for your class test 3, sorry. So the first test for this semester, class test 3, will finish on what we cover today. Okay, with the area problem. I did send an email this morning with the breakdown for the test. So that last thing on finding the area under a curve, it's from what we do today. Okay. Then next week, we're going to continue with finding the area under curves for other functions that will not be in the test. Okay. It might be in the exam, but it will not be in the class test. Okay, any of the tests this semester. Okay, any questions on that? You're all good. Okay. So please carry on reading here for the area problem. And then for next week, Thursday, the definite integral, the 5.2. Okay, so if you're reading ahead, please read 5.1, 5.2 for Thursday, and then for next week, Monday. Right. Any questions before we start? They're all good. Okay. So let's start. So what is the area problem? Okay, so given some function f, we're not going to assume if it's continuous or differentiable just yet, so just some function f. What we want to do is find the area below the function, but above the x-axis, between some a and b points. So we can do a rough sketch like this. So let's say we have our function f. That's okay. So we got some function f here in pink. Again, I'm drawing it, continuous, differentiable, but please keep in mind we're assuming any function for now. Okay, so the pictures will be nice and differentiable and so on, but we'll see later on that that is not a strict requirement. Okay, it's just for the picture. So we want to find the area between x equals a and x equals b. Okay, so from some start point to some end point, what is the area below the function but above the x-axis? In other words, the shaded part here. Okay, so the area problem can be stated as finding the area below the function but above the x-axis between x equals a and x equals b. Okay. So this lecture, we're going to look at how do we find this area here. Okay, so the main idea that we're going to be using is to take this might be complicated area, right? We don't know what f looks like. It could be pretty complicated, and chop it up into smaller parts that are hopefully less complicated. Okay, so we're going to take our function. Again, let's say it looks something like this. Okay, again from x equals a to x equals b. And we're going to chop it up into smaller parts. So we're going to chop it up into rectangles because that seems pretty easy, right? If we know the area of a rectangle, we can find the area of the shape if we chop it up like that. Okay, so the idea is to take the interval from a to b, chop it up into rectangles, and we get the following picture. We get something like that. So we cut it up and we get the following picture here. So we're going to assume that each of these rectangles have the same width. Okay. So the little width at the bottom there, we're going to assume that all of those are the same. We're going to call that delta x. Yeah, that will be the width of one of these rectangles. Then the height of the rectangle, well, that's just the function value at that point. So let's say at this point over here, the function has the value f of x. Well, then that will be the height of that rectangle there. So the area of that rectangle that we singled out there is just going to be base times height. Yeah. So if the base is delta x and the height is f of x, at that particular rectangle, the area will be f of x times delta x. So again, we select this particular one here. This area, let's call it delta A, will then be f of x delta x. Okay, for that particular one. Now notice that if we add up all of these rectangle areas, we get an approximation for that area. Okay. If we add up all the rectangle areas, right here we just selected one of them, but we can do it for all of them. If we add up the rectangle areas, then we get an approximation to the area. Okay, so why do I say approximation? Well, notice on the left here, this rectangle over here, that area is a little bit smaller than where the function actually goes up to. So let's put that in blue here. This little bit in blue is not covered. Yeah. So if we look at that bit, that rectangle is a little bit smaller. Yeah. And there's a little bit of blue there. That is the error, right? It's not covered by the rectangle. So here we have an error, right? It's a bit smaller than what we need. And if we look on the right over here, let's say this rectangle, let's put this in green here. We see this rectangle is too big. It covers more than the area that we need. And again, that has some error to it. So again, on the left, that rectangle is the blue there. That is too small than what we need. So there's a little bit of error. On the right, that rectangle is too big. It covers more than the function. And again, we have a little bit of error there. Okay. Now, the idea with these rectangles is that if we make them smaller, then the error where it's a bit too small or it's a bit too big will get smaller. So the main idea is that if we make the rectangles smaller, if we make the rectangles smaller, or equivalently, we just fit more of them in that space. So here we had 1, 2, 3, 4, 5, 6 rectangles. If we tried to fit in 10 rectangles, right, they would be smaller, right? Because you have to fit it in the same space. So either we make them smaller, or equivalently, equivalently add more of them. Then the error will decrease. Okay. And by error, again, I mean that little blue part on the left and the green part on the right. So the blue error and the green error. So where there's an underestimate and where there's an overestimate, those two errors hopefully go to zero. Yeah, again, the blue, that was an underestimate because it's smaller than what we need. The green error, that was an overestimate. It's more than what we need. Okay, so let's draw the picture again with smaller rectangles and see if this actually works. Right? If the error stays the same, if we add more rectangles, well, that doesn't really help us. Okay, so let's check. Okay, so I'll try copy this the same. So from x equals a to x equals b, that was somewhere here. Okay, so we're going to zoom in a bit and add more rectangles, or equivalently make them smaller. Okay, so we'll just add 2 over there. So we see here from the beginning, we had this one rectangle over here with this area in blue. That was the underestimate. We split it into 2 rectangles and we get this new error. A little bit over there. So you see we doubled the amount of rectangles in that region and the error got smaller. Okay, so the underestimate in blue, that got smaller. We can do the same thing for the overestimate. That green one over there, we're going to make those rectangles smaller. See what happens. So that was somewhere over here. Okay, again, I took the one rectangle and I split it into 2 smaller ones. And we see that the overestimate in green is now this bit. Right? It's much smaller. Therefore, by adding more rectangles, in our case, we doubled the amount. The overestimate and the underestimate in both cases, those were the errors, got smaller. Okay. Now, the hope is that if we add more and more rectangles, the error goes to 0. And in the limit of adding infinitely many rectangles, then the error will be 0. Okay, so adding more rectangles, the error goes to 0, and then in the limit, it is 0. Okay, that's the idea. So in the limit of adding infinitely many rectangles, or let's say n goes to infinity, so n, that's the number of rectangles we're adding. So in the limit n goes to infinity, the error equals 0. Okay. Now, we're not going to be proving this. That is beyond the scope of the course. So we'll just believe me when I say that we take the limit, we get 0 error. You won't be required to prove that. Okay, so let's set up this limit. Okay, again, you won't be asked to prove it, but you will be asked to do the calculations for the limits. Okay, so we're going to set it up. What do we need? Well, the idea is to find the area of each individual rectangle, like we did over here. Okay, we find the area of each individual one, add them up, and that will be the total area. Okay, so let's say capital A sub n, that will be the area, the total area, if we have n rectangles, like we drew in the pictures. So this is going to be the sum. Please make sure you know your sigma notations. The sum from I equals 1 to n, so over all of the rectangles. We need the height of the rectangle, and we need the width of the rectangle. We said the height was f of x. So at the rectangle I, we're going to call the height f of xi at that point. And the width we said was the same for all of the rectangles. We called that delta x. Yeah, so it's just a little bit of side working. That delta x, we said that was the width. It's the same for all of them. We can calculate that as b minus a over n. Because b minus a, that was the full width. If we chop that up into n rectangles, then each one will be b minus a over n. Right? Quite simple. Now, what about the x value? If we go back here, this x value over there. Well, we're starting at x equals a, and we're hopping over some integer amounts of rectangles. So we start at a, and then the next rectangle will be a plus delta x. It's the width that we're hopping over. Then the next rectangle will be a plus delta x plus another delta x, because we're hopping over full rectangles at a time. So xi will be a, that's our starting point, and we're at the ith rectangle, so we've hopped over I rectangles. So it will be a plus I delta x. Is that confusing anyone? Okay, so we start at A. If we want to go to the first rectangle, the step, then it will be A plus delta x. If we want the next one, it will be A plus 2 delta x, because we're hopping over 2. And then 3, and then 4, and so on. Okay, so we just substitute these in. So delta x, we know that is the width. Xi, that's the position of the rectangle. We sub that in, that gives us the height of the rectangle, and the product, that is the area. Okay, straightforward. Now this is just for n rectangles, right? The hope was that in the limit of n goes to infinity, the error goes to 0, and the area becomes the exact area that we're looking for. So we say that A is defined as the limit as n goes to infinity of an. Okay, and then we can substitute. So this is equal to the limit as n goes to infinity. The sum I goes from 1 to n, f of xi delta x. Okay, please put a big box around this. And a big exclamation mark. You will be required to know this formula, so that won't be given to you. So please put a big box around and something to show that it is very important. Okay, yeah, you will need to memorize that. Now, just a little bit of terminology before we get to the examples. Okay, so this is just some wording. It's not so important for our calculations, but you will see this in the textbook and YouTube videos and so on. This A sub n, the sum that we have here, that is called a Riemann sum. A sub n, sometimes called R sub n, is called a Riemann sum. Okay, it's just named after the guy that came up with it, so you will see that quite a lot. Okay, and secondly, A, which is the limits of that A sub n, also called R, again, the limit of R sub n, is called the limits of a Riemann sum. Okay, so just a bit of terminology. So if you see these words in the textbook or online, you know what it means. Okay, so A sub n, that is the area with n rectangles. That is called a Riemann sum. And then the full A, after we take the limit, that is the limit of a Riemann sum. Right, it's just terminology, nothing new there. Okay, and then finally, definition. Okay, the exact area under f of x between x equals a and x equals b is defined to be the limit of the Riemann sum. Yeah. So the area, whatever it might be, is actually defined by this limit of the Riemann sum. Okay, we call that the exact area. If you don't take the limit, then that is just an approximate area. Okay. Any questions so far? Yeah, pretty simple. And then just a few things you might have forgotten from high school with the sigma notation. So there's three formulas we're going to go through today for the polynomial functions. And then there's some other formulas you probably wouldn't have seen in high school. We'll cover that on the Thursday. Okay, but these ones you have seen before, so it's just a reminder. The sum I equals 1 to n of 1. So it's just 1 plus 1 plus 1 plus 1 and so on. That's just n. The sum I equals 1 to n of I. So 1 plus 2 plus 3 and so on. That is going to be n plus 1 over 2. I hope you've seen this before. Patterns or something in high school. Okay. Then we have the sum I equals 1 to n of I squared. This was the funny one. n plus 1, 2n plus 1 over 6. And then the last one that we will need, the sum I equals 1 to n of I cubed. This one's easy. It's whatever we had for the I, but we just square the whole thing. Okay, so it's whatever you had for the sum of I, you square the whole thing. That's for I cubed. And remember before I said for these, we are only going to go up to cubics. I think I said it before. This is what? We only go up to the sum of I cubed. Yeah. So I to the 4, I to the 5, and so on. There is a summation for that. So the sum of I to the 4, you can work it out. I to the 5, you can work it out. But that will not be tested. Okay. So it's only these ones. So constant I squared, I cubed. So linear, quadratic, cubic polynomials. You're expected to know these formulas. Anything after this, you are not expected to know. Okay. And by that, I mean these are not given to you. Okay, you need to know these. Okay, so please make note for assessments. Okay. So it's this formula over here in the box there. You have to know that one. That is not given. And then these ones, if you don't know them from high school or you forgot them from high school, please learn them again. Okay, it will not be given. Right. Any questions on these before we get to the example? All good. Okay. Then on Thursday, we're going to cover the summation for trig functions and for exponentials. Okay, you definitely did not cover that in high school, so that will be new for Thursday. Okay. Examples. Okay, so the working for these problems is quite long. There's a lot of individual steps. The problem is at each step, right, there's room for mistakes. If you make a mistake on the first line, unfortunately, it carries on, right? Line after line, it carries through, and then your final answer will be wrong. Okay, and then you kind of just hope for part marks along the way. Okay, so I'll point out all of the steps that we need to follow. Again, there's quite a few, but if you go through it slowly, you'll be fine. In the quizzes, tests, exams, and so on, these will all be out of 10. Okay, because it's quite a lot of working to get through. Now, if you think about it, your final exam is out of 100. This one question is out of 10. 10% for your exam, just on the one question. Okay, so when I say please go through it slowly, look at the steps, I don't mean for now, I mean for your exam. Okay, go through it slowly and check. It's 10% of your final mark. Okay, so example number 1. We have f of x is equal to x squared. So just a simple quadratic from x equals 1 to x equals 2. So that's the setup for the problem. We have some function. We want to find the area below the curve from x equals 1 to x equals 2. You will not need to draw any pictures of this. Okay. So this question is just calculating. Other questions later on, you will be required to sketch the regions and so on, but that will be later. Okay. For these ones, it's just calculating, no sketching needed. Okay, so no sketching needed. Right, there's plenty of other questions on sketching these. So the first thing we need to do is remember our formula and the pieces that we need to substitute. So we go back here. Okay, so this was our formula, limit of the sum, and these were the pieces we needed to calculate to substitute. So the first thing we calculate is delta x. So b is given, a is given, n, we're going to take the limit later. We calculate delta x. That's the first thing. Second thing, once we have delta x, we can then calculate xi by substituting. Once we have xi, we can then calculate f of xi in that order. And again, the problem, if you make a mistake with delta x, you're substituting the wrong thing into xi, and then you're substituting the wrong thing into f of xi, and now you're taking the limit of the wrong thing. You see how it gets worse with each thing. So at each step, please check your working before you substitute for the next step. Okay, so let's call this step 1. Okay, we calculate delta x, we check our answer, calculate xi, check our answer, calculate f of xi, check our answer. So delta x, b minus a over n, so that will be 2 minus 1 over n. Okay, so 1 over n, easy enough. Then we need xi. That will be a plus I delta x. A is 1, so we put 1 plus I. And then delta x we calculated just a bit before. That will be 1 over n. Yeah, all good. And finally, we calculate f of xi, which is x squared. Sorry, that's an n there. We need to square this out. Yeah, for the other polynomials, maybe we have to cube it and so on. So just be careful with that. Okay, again, only up to cubed, not fourth or fifth or so on. So this will be 1 plus 2i over n plus I squared over n squared. Yeah. So step 1, calculate these. Done. Step 2 is to then take whatever we calculated here and substitute into that formula. Again, you need to know that formula. Okay, so step 2, a equals the limit, n goes to infinity, the sum I equals 1 to n, f of xi delta x. Okay, you just write it out a few times, you have it memorized in a day. Okay, so let's substitute all of that in, and then we'll work on the summation, and then we'll work on the limit. So this is going to be the limit, n goes to infinity, the sum I equals 1 to n, f of xi, let's put that in brackets because we've got a few terms there. So that will be 1 plus 2I over n plus I squared over n squared. And now what a lot of students forget, because they're in a hurry and so on, the delta x at the end. So please put a star here. Okay. A lot of students forget the 1 over n at the end, and then everything gets messed up afterwards. Okay. Now you might think, oh no, it's obvious, you put the 1 over n, right? You're writing your exam, you're under a lot of stress, very easy to forget. Okay, so just make the star there so you don't forget. Okay, once we've substituted everything, we're going to take that 1 over n, the delta x from the outside, and distribute it onto each term. Right, I'm not going to write down the explanation for each step, but if you want to make a little note, distribute and so on, just make a little note on the side. So we're going to distribute the delta x. So that will be 1 over n plus 2I over n squared plus r squared over n cubed. And here, if you're going to end up with a mess or not. Whatever the exponent for I is, the exponent for n is always one more. Always. Okay. So we see at the top, we have I. At the bottom is squared. At the top is squared. The bottom is cubed. If you do not have that, you're going to run into serious problems later on. Okay. So always just check. If you don't see that, it means you did not distribute the delta x. Okay. So again, check that. Next, we're going to split up the sum into 3 individual sums. If you have 4 terms, you're going to have 4 sums, but we split it up individually. Okay, even if you think you're super smart with summations, follow the steps. So this is going to be the limit, n goes to infinity, and we're going to split it up into individual ones. And we know our summation rules. Anything that's not I, we can take outside of the sum. So for the first term, we have 1 over n. That has nothing to do with I. We can take that out. Next term, 2 over n squared. Nothing to do with I. We can take that out. Last term, 1 over n cubed. Nothing to do with I. We can take it out. Okay, so we end up with 1 over n. The sum I equals 1 to n of 1. Plus, for the next one, 2 over n squared. Nothing to do with I. We take it out. And the last one, 1 over n cubed, nothing to do with I, we take it out. Yeah. So now we have 3 separate sums. If this was 4 terms, you'd have 4 sums. If it was 5 terms, you had 5 sums and so on. But we end up with this. Notice that each individual sum, ignore the thing in front, is exactly what we have over here. Yeah. So we have the sum with I, the sum with r squared, if we have r cubed, and so on, just by itself. Okay, nothing else there. So we got this one, we got this one, and we got this one. Anything else we put in front, we don't care about that. Okay, again, even if you think you're super smart with summations, follow each step, right? Now we can substitute. So that was step 3. Okay, so step 3, we replace the summations with whatever we had over here. So the sum of 1, we replace with n. The sum of I, we replace with n plus 1 over 2. Each term we replace from this list. Okay, so the limits, n goes to infinity, all of that stays. 1 over n, that stays. And now the sum of 1, that's just n, so we replace that. 2 over n squared. The sum of I, we replace that. And the sum of r squared, we replace that. Okay, so again, the green underlined, that became this. The blue underlined, that became that. And the pink underlined, that became all of that. Yeah, just a replacement from what we know. Next, we're going to simplify. And then finally, we're going to take the limit. So step 4. Okay, we're going to simplify top and bottom and expand out if we need to. Right, I said a lot of steps, so this is why. So we have the limit, n goes to infinity. Okay, we simplify as much as possible and expand out if needed. Yeah, n over n for the first one, that will just be 1. Plus. Next one, again, simplify as much as possible and expand out. So at the top, we have an n by itself. At the bottom, we have n squared. So we can put n at the bottom. And then we have 2 at the top, 2 at the bottom. That can cancel. So we're left with n plus 1 over n. Okay, the 2's cancelled, and then one of the n's cancelled. Okay, you cancel as much as you can before you get to the next step. And then the next one, plus, we have the 1 over 6. We can just take that out for a bit. We've got an n at the top with those brackets there. And then at the bottom, we have n cubed. So there's an n squared left over. We can put that at the bottom. Yeah. So that's the cancelling done. Now we're going to do the separation. So for each of these fractions, we're going to split them up into individual terms. So when we get to step 5 and we have to take the limits, everything is super easy. If you want to skip a step and go straight to the limit, that's fine. If you get the right answer, you get it. I don't mind. But if you want to show every step, splitting up, taking the limits, that's fine as well. The time allocated does include that. Okay. So if you want to do it the longest possible way, you do have the time for that. So let's do that. We're going to split this up. So this is going to be the limit. N goes to infinity, 1 plus n over n, that will be a 1. And then 1 over n, that's 1 over n. Okay, plus. Next one, we can expand out the brackets and then simplify. So we get the 1 over 6 still. We get 2n squared over n squared. So 2. Then we get 3n over n squared. So that's 3 over n. And then we get 1 over n squared. Just write it 1 over n squared. Okay. So we expand it out and wrote it all separately. Now, when we take the limit, it's very easy. Because n's at the bottom. When n goes to infinity, 1 over n goes to 0. And we can just cross off anything with n now. So that goes, that goes, that goes. So much easier. If you expand it out, you just cross out everything with n. If we didn't do that, we look at the previous line, n over n plus 1. The top becomes infinity, the bottom becomes infinity. You have to do L'Hopital's rule or something to figure that out. And then the other one over there, we have 2n squared at the top, n squared at the bottom. You know we can take the highest order term and so on. Rather be safe. Yeah. And step 5. Okay, once we're done with all the cancellation, we just add up whatever's left. So we've got 1 plus 1, so there'll be 2 plus a third. Okay, so there'll be, what's that, 7 over 3. Okay, 5 steps. So roughly, not quite because of part marks and stuff, each step is about 2 marks. Again, roughly, there's some half part marks and so on. But if you follow the 5 steps, you can expect 2, 2, 2, 2. Okay, so first step, find all the bits that we need. 2 marks, again, roughly. Substitution. So subbing everything in, expanding out, another 2. Knowing your formulas to do the replacements, another 2. Doing the limit and final answer, another 2, and then the final 2. Okay. Any questions? Okay. I know it's a lot of steps, but each step was pretty easy, right? So, okay, you better not say no or else you're in trouble. But I mean, substituting in, that's easy to do on its own. Substituting the formulas, that's pretty easy to do on its own. You just need to make sure that you're doing it right step by step. Yeah. So that's going to be it for today. I don't want to scare you with too much just yet. But there's 2 homework problems you can try out, and then we'll continue on Thursday. Just quiet, please. Just a note for the tutorials. I think the tutorial problems, there's like 20 questions there. Please do not do all 20. After 5 of them, if you're getting everything right, do something else with your time. Okay. No, there's a lot of problems, but I mean, if you're going to do all 20 and it's very easy for you, following the steps, please do something else. Okay. You'll see. After doing the first 5, if you get it, you get it. If you don't, then you do more. Okay. So homework problem number 1. F of x equals x minus x squared from x equals 0 to x equals 1. Okay, so you got your A, you got your B, you got your F. You know what to do there. And then number 2, f of x equals 1 plus x cubed. So you see this cubed over here, that will end up being an I cubed when we do the sum. Okay, from x equals 0 to x equals 2. Okay. So give yourself about 20 minutes to cover those 2. If you're spending more than that time, then there's some issue with you remembering things and taking too much time. Okay. No. Okay, right. It sounds funny now, but when it comes to the exam, right? You have 3 hours, that's all you get. If you're going to spend half an hour on a 10-mark question, maybe you're leaving stuff out later on. 20 minutes, if you can do that, you'll be good for Thursday. Right. Any questions? Yeah. That doesn't matter. Yeah. No. There's no sketching, turning points to worry about. It's just the function from one point to another point. Whatever happens in between, we're not worried about that just yet. Next week, we will be worried about that. Right. Any other questions? Well, good. Okay. We'll see you Wednesday.